Good afternoon. Welcome to the CERIAS Security Seminar at Purdue University. It's my great pleasure to introduce today's speaker, Professor Alex Liu. Alex is currently an assistant professor in the Department of Computer Science and Engineering at Michigan State University. He received his PhD degree in computer science from the University of Texas at Austin in 2006. He received the IEEE and IFIP William C. Carter Award in 2004 and the National Science Foundation Career Award in 2009. And his research interests are in networking, security, and privacy. Today he'll talk about regular expression matching using TCAMs.
Okay, thank you very much, Ning, for the introduction. So it is my great honor to share with you our research results. So today I'm going to talk about regular expression matching for using TCAMs. So a packet consists of a header and payload. And the mechanism for checking packet header is called a packet classification. This is used in router access control list and firewalls. And the mechanism for checking packet payload is called deep packet inspection, short for DPI. And so there are many applications for DPI. So for enterprises, for example, they can use DPI for detection of viruses and worms on intrusion detection systems and the intrusion prevention systems and application firewalls and so on. And also can be used for data leak prevention. So for example, if you send out an email, you're working in a company and you send out an email with some confidential file attached, and they can use DPI to figure this out and may take further actions. It can also be used for load balancing in data centers. For example, they use layer 7 switches. And for internet service providers, they can use DPI for copyright enforcement. If you are sharing with copyrighted material or transmit them over the network, they can figure that out using DPI. And also quality of service, they can use DPI to figure out what kind of applications are running, and then they give different priority to different applications. For example, they may give higher priority to voice over IP traffic. And also they can use a DPI for usage monitoring, so what kind of applications are running on my network. And targeted advertising. For example, if they collect your web browsing behavior and figure out what kind of interest you have, and then send you targeted advertisement. And for government, for example, the US FCC requires that all the ISPs need to have the DPI capability when the court orders monitoring some users. The ISP can provide DPI for the traffic going out and going into those users. So the DPI technology in the past is mainly string matching. So currently they use regular expression matching. So because regular expressions have much more expressive power than simple strings. For example, like snort, burrow, and tipping point, those commercial DPI technologies, they use regular expression matching. So the problem is you are given a set of regular expressions, and so how to quickly scan the packet payload to determine which regular expressions you may have are matched. So this one payload may match multiple regular expressions. So that's the problem. So here, so previous regular expression matching algorithms are either software-based or hardware-based. And there are many advantages for software-based algorithms, and here I focus on the arguably disadvantages. So basically, one problem is, for example, they have to be implemented on customized ASIC chips to achieve high throughput. And using ASIC chips, this will incur high deployment cost, and also they are hardwired to a particular algorithm. If you later change your algorithm, then you have to throw the system away and burn new ASIC chips, then design new systems. And another category of regular expression matching algorithms are FPGA based. So of course there are many advantages. So here I just focus on the disadvantages. So one problem is updating regular expression rules for FPGA-based algorithms is quite difficult. They really require resynthesizing and updating that FPGA circuitry, and so quite often this requires manual inspection, and it is slow and difficult. So our approach is very different from previous solutions. So we propose the first ternary content addressable memory-based regular expression matching solution. So this ternary content addressable memory is short for TCAM. So every bit in a TCAM is 0, 1, or star. So there are 3 possible values. It's unlike normal memory, it's either only 0 or 1, right? So so given a lookup key, so basically the TCAM hardware will compare this lookup key with all the entries in TCAM in parallel, and then return the index of the first match. So take a look at this example. Suppose this is the TCAM lookup, this TCAM layout. For example, if you give the key, say 1110, 1101, you will see that this entry can match the second one, because the star can match 0, it can also match 1. And similarly, it can match the third entry and also can match the last entry. So however, the hardware basically first find all the matches, and then they use a priority encoding. This will return the first match. So the return will return the index 2, and based on index 2, they can quickly find this corresponding decision in SRAM. So every TCAM chip itself has TCAM circuits, and also have associated SRAM circuits. And the TCAM used to basically store the rules, and the SRAM used to store the decisions. And there's a one-to-one mapping between the TCAM entries and SRAM entries. So compared with the traditional memory is the lookup process is kind of reversed. So the traditional memory, you give the input is the index, right? You find you give the index, and output is the entry. But here, for such memory, is you give the entry, and output is the index. So, and TCAM chips has been widely used in routers and IDS, IPS, and so on. So the most popular use is for packet classification. Go ahead.
So do you also store the priorities along with the strings that you can? Because is it like the earliest match first, or is there an explicit priority there?
You don't need to store any information about the priority. They basically based on the first match. So basically, if you store this entry before the other entry, this entry will have higher priority than any entry below you. Yeah. Okay. So there are 3 main advantages of TCAM-based regular expression matching solutions. So one is speed. It is a constant time lookup. No matter how many entries you have. So for example, in our experiments, we use a 2.36 megabits TCAM chip. We can achieve the maximum is 18.6 gigabps. And storage is also TCAM. Actually, they are capable of storing large deterministic finite automata. So typically, algorithm for regular expression matching is they convert the regular expression set to a DFA, and then process based on the DFA. So here, but this requires many optimization algorithms to achieve this goal. So in our experiments, we can use say 0.56 megabits TCAM to store a DFA with say 25,000 states. And another advantage is easy to deploy. So because the TCAM chips are off-the-shelf chips, and actually many of those routers and IDS, IPSs, they already have TCAM in the system. So there are 2 key technical challenges, 2 overall technical challenges in TCAM-based regular expression matching. So one is encoding a large DFA in a small TCAM is very difficult. So the straightforward solution, so which I will go over that, with the DFA with say 25,000 states will require 140 megabits TCAM, and the largest TCAM available on the market right now is 72 megabits. And also, larger TCAM will lead to more power, more heat, and more expensive, and also very actually, larger TCAM will also be a little bit slower. So smaller TCAM will be faster. So just a single chip, TCAM chip, if you it costs a lot of power. For example, in the routers with TCAM, the TCAM itself costs about 10% of the whole overall power. And so we have two ideas to address this challenge. One is transition sharing, and another is table consolidation, which I will go over in this talk. And another technical challenge is improving the regular matching speed is quite difficult. So typically using this DFA, so at every lookup we can consume one character. So if you want to improve speed, so you have to consume multiple characters at a time. So this if you build a DFA consume, let's say, k characters, that's called k stride DFA. So will be basically every edge will in the DFA will consume k characters. So however, k stride DFA leads to exponential increase in the number of states and the number of transitions. So, and our idea is called variable striding. So at every step we consume a variable number of strides. So without exploding the space. So let's first take a look at the very basic TCAM-based regular expression matching. So this is a very simple DFA. So basically, we first convert a regular expression set to a DFA. So there are standard algorithms to achieve this, to do this conversion. And then for every state, we can generate a transition table of 256 entries. Here we assume every character is 8 bits. So then you will have 256 entries, right? And then for every state, we can generate a unique ID. And then we concatenate, we basically, for every entry, we can concatenate this entry with its corresponding state ID. And then we can concatenate all these tables together, right? So for example, we have S0, S1, S2, so we have 3 states in this simple example DFA. And we have 3 tables. Every table is 256 entries, and the source state ID is all different. And we have another column in the SRAM. We'll have destination IDs. So let's look at the lookup process. So suppose I got a string of, say, AAB. First, for every DFA, there's a starting state. So the starting state in this case is 0. So is S0, which is the state ID 0, 0. And then A is 1, 0, 1, 1, 0, 0, 0, 1. So I concatenate the state, the current state ID plus the current character. And then I perform a lookup. It will map this entry. And then I get the destination ID. Then the second character is A, and then this destination ID will become the current state ID. And then I put A here again and do a lookup. So this destination ID is 10, and I concatenate this 10 with B again, and do a lookup. And so that's will be the final result will be 0, 1. Will be getting to 0, 1. State 0, 1, for example. So this very basic solution works, but it will consume too much TCAM space. For example, if you have 25,000 states, will consume 140 megabytes. Will require 140 megabytes TCAM. So that will be too big for to build this system. So our first idea for minimizing TCAM space is called transition sharing. And we have, within transition sharing, we have 2 sub-ideas. One is character bundling, and another is shadow encoding. So let's first take a look at character bundling. So the basic idea is to merge common transitions within each state. So the basic idea, we want to use the ternary entries on the input character column. So there are 3 columns, right? You have a current state column, and you have input character column, and then the lookup result will give you the destination state ID. So the observation is based on that in one state, so there are many transitions, they go to the same destination state. And actually in our experiments, that shows that for most states, there's only 2 or 3 unique destination states. So first I will use an example to show this, combining, this merging is possible. So take a look at these 2 entries. These 2 entries, they're all in the same state table, S2. And if you look at the input character, they only differ by the last bit. Last bit, one is 0, another is 1, right? And they go to the same destination state. So we can, right now, this TCAM entry or binary right now, actually we can replace by ternary. So this will be, we can combine these 2 entries together using, replace the last bit by star, right? This star will match both entries. So that will save TCAM space, right? So this is just a simple example that illustrates that this is possible. But the algorithm is much more complex than that. So the algorithm to achieving this purpose is we use a one-dimensional TCAM minimization algorithm. So there are previous algorithms that we can use. So by this technique, so for this example, we used to have 768 entries. Right now, we can reduce it to 11 entries. So in practice, so this technique itself will result in about 80% to 95% of reduction in terms of TCAM space. So take a look at state table as 0. So these 2 entries will encode A to O, for example, and these 2 entries will encode else. So the second idea for TCAM minimization is called transition sharing. So the basic idea is we want to merge common transitions among states. So we basically want to use ternary entries on the current state column as well. So the basic observation is that there are many states share common transitions even after we do the character boundary, right? So take a look at this example. So after character boundary right now, so we take a look at these 2 states, S1 and S2. So if you look at the first entry of each table, so you will discover that they only differ in the source ID field, source ID column. The input is the same, and the destination ID is the same. So, and also similarly for the rest of these 3, these 2 red ones, they only differ in the source state ID. These 2 blue is same thing. These 2 green also only differ in the source state ID column. So the basic intuition is that is it possible that we can remove these 4 entries from state S1, such that we can let S2 to take care of those rules. So, however, if you look at this right now, it's impossible because the source state ID is 0, 1, and source state ID for S2 is 1, 0. If you specify 1, 0 by 1 star, this rule 1 star doesn't match 0, 1. And if you replace by star star will match 0, 0, that table also. So the good news is that the state IDs, we can assign them arbitrarily, right? State IDs, you can assign them in any way you want. So if we do a replacement, if we assign the IDs carefully, so for example, we assign S0 by 1, 0 instead of 0, 0, for example, S1 by 0, 1 and S2 by, S1 by 0, 0, S2 by 0, 1, you will see that after this replacement, what will happen is that the source state ID for S1 is 0, 0, and the source state ID for S2 is 0, 1. So if we replace the source ID field in S2 table by 0 star, so 0 star only match 0, 0 and 0, 1. So if we replace that, then we can remove all these entries from table S1. Right? If you replace those, so you can see that for this will be the result of the removing those entries from state S1. so the lookup key that previously, for example, if the lookup key previously matched, say, look at say the third entry. If you let's look at the first entry. So the previous lookup key that matched the first one in the in the left will be source ID to 00 and input is 01100000, and this lookup key will not match the first entry in S1 after we do this after we remove these entries, but it will match the first entry in the S2 table. So this S2 table, the destination is because 0 star will match 00 also. So the destination ID will still be 10. So basically, we want another table to take care of the lookup for the tables above it, right? So by changing the source ID field to be ternary. So there are three problems for realizing this. So one is how to find the best order of the state tables. So you need to order them carefully. And the solution we use is delayed input DFA. This is called D2FA. This is proposed by Kuma and so on, assured by in 2006. They proposed this for software-based regular expression matching. And the second problem is how to carefully choose the binary IDs and ternary codes for each state. So we have a shadow encoding algorithm. And the third problem is how to remove the deferred TCAM entries. So how to remove entries from tables, such that the table below it can take care of those removed entries. So we have an optimal incomplete one-dimensional table minimization algorithm. Take a look at the running example. For the running example, after we do this shadow encoding, so right now we reduce the number of entries from 11 to 7. And in practice, this will result in about a 85% to 97% reduction on top of character bundling. So the total reduction by both character bundling and the shadow encoding is over 99.5% reduction. Yes?
So Alex, depending on how you map the old IDs, state IDs to the new state IDs,
that's correct.
You will
get
different kinds, different reductions.
That's correct. That's correct.
Presumably you don't do a brute force search from the old space to the new space.
No, we don't. I will go through how do we assign these IDs. That's a very good question, and that's the whole idea of that's this algorithm all about. How to assign those IDs is non-trivial. Yeah. So take a look for example, after we do this shadow encoding, this is the table with 7 entries, and take a look at this one lookup. Suppose currently you are in state S1, and the input is W, character W, for example, and this is supposed to match an entry in the table S1, but S1 many entries are deleted, right? So you will see that doesn't match S1, doesn't match S2, it will match an entry in S0. And the destination ID is 10, and that is correct. So first of all, let's try and see how to order the state tables. So we want to find the best order for these tables in the TCAM, because the order will affect how do you encode them and how many entries can be deleted. So we first build a delayed input DFA. So basically, we construct a complete graph called the space reduction graph, and with the DFA states as nodes, and the edge width is equal to the common transitions between these states. So and the result turns out that basically the edge width basically we build a complete graph. So I need to so every node in this graph is a state ID, and the edge weight is the number of common transitions between these two states. And this distribution of the number of common the weight is bimodal. So basically, either very small, less than 10, or very big is more than 180. So we use cutoff. We choose 10 as a cutoff for our experiments. We basically delete edges with low edge width. So then we get basically a forest. And then for this forest, we build a maximum spanning tree, and then we use the self-loop states as the root. So the basic algorithm is similar to the one that originally proposed in the D-square FA paper, although with some different optimization choices. The optimization choices are different. So in that the idea of the D-square FA paper, the basic idea is every edge right now is there are 256 possible outgoing edges. So that's too many. So if we want to reduce it, so how to reduce it? The basic idea is if these two states share many common transitions, I would just delete the common transition from this state, and then when I reach this state, if I got a character that's that's one of those deleted transitions, I will have an epsilon transition go to this state, and this epsilon transition will not consume any character, and then this state will take care of that, will consume that character. And this can be, you may have multiple deferments. So this will in the DFA original DFA scheme, D-square FA scheme. So basically, they have a speed penalty because you may have traversed the D-square FA without consuming any character for multiple steps. So, however, using TCAM, because of we using the first match semantics, so this basically traversing these different states in TCAM is free. So we don't every step we still consume one character. So we don't have any speed penalty. For example, in this case, basically, for example, 5 will this state 9 will defer to 5, 5 defer to 4, and for self-looking state, basically the state that half of the outgoing edges point to himself. Yeah. So and come up with the ordering. Basically, you can do a depth first traversal from this forest. And next is basically after we build this deferment forest. We know that okay, 1 defer to 2. So for this example, we know that 2 will defer to 1, 5 defer to 3, 3 defer to 1. We know this forest. Now we need to assign binary IDs and ternary shadow code for each state. So basically, the binary IDs will be, so every state has two code. One is binary, which is called a state ID. So this will be used in a destination state column. Destination, remember, is in SRAM, so it is binary. And it also has a shadow code, which is ternary. This shadow code will be used in the source state column. So the shadow code of every state needs to satisfy 2 conditions. So one is the shadow code of every state needs to match all the binary IDs and ternary shadow codes of all the states in a subtree. For example, the thing that we colored by light blue. So 1 0, the shadow code is 1 0 star star. Need to match all the binary IDs and shadow codes in his subtree. And similarly, and another property is that the shadow code of every state doesn't match any binary ID or the ternary source code of any other states, of any other siblings and their corresponding children. So basically, we don't want to accidentally this entry will be matched by another state that's not correct. So and the binary IDs and ternary codes all need to be unique. So given valid shadow encoding, shadow encoding, so every state satisfies two properties. Every node satisfies two properties. So one is the binary prefix space in its shadow code must be the prefix of all the binary ID and source code of the shadow code of all its states in its subtree. For example, take a look of this one. So the state, let's take a look of state 4. State 4, you can see the shadow code is 1 1 star star. So the prefix space is 1 1, and this 1 1 will match all. Will be also the prefix of all the shadow codes and binary IDs of all the states in its subtree. And the second property is that the star base will form a valid shadow encoding for the subtree rooted as at the child. So let's take a look at this example. For this 3 and 5, you can do, if you look at 3 and 5, if you delete all the prefix space, then we will have shadow code for 3 is star and ID is 0, and shadow code for 5 is 1 and ID is 1. So this also form this will also form a valid shadow encoding. And same thing for this subtree by states 5, 6, and 7. So basically, this will suggest that the shadow encoding algorithm can be recursive. So we developed a recursive shadow encoding algorithm. Let's first take a look at the basic shadow encoding algorithm. So in each step, basically the current root does the following. So assuming so. Basically, first it recursively calls on each of its children to compute the shadow encoding for its own subtree. So, for example, we are talking at the level of state 1. So it has 3 subtrees, right? It has 3 subtrees, and we do this for 5. The subtree 1 is 1, 2, and another is 3 and 5. We're missing one edge, and also this subtree is 4, 6, and 7. We first do this encoding, shadow encoding for every children, and then second is we assign a unique ID to each of its children and itself. So basically, we look at 1, 2, 3, and 4. We can assign a unique ID. So the simple unique ID is just a binary encoding, right? So you have 4 nodes, then you can use 2 bits to encode this. For example, we assign state 0, the ID is 0, 0, and assign 2 is 0, 1, and source the state 3 is 1, 0, and source state the state 4 is 1, 1. Then so basically, and then we can, because the source shadow code of state 4 is 4 bits, so then we need to padding with 0. So basically, this 0, this 1, 0 star, this for state 3, we need to insert a 0 there. So, and then this will basically, the IDs assigned to every children will propagate to all the states in the subtree. So this will form a valid shadow encoding. This will be a valid shadow encoding. So you can see that the property is basically binary ID of any node will the binary ID of every node, it will match its own state. It will match its own shadow code, and also match the shadow code if is father, and match the shadow code is grandfather, and so on. Yeah.
So what happens if you add a new firewall rule that may disturb your entire tree? It won't be a local change.
Oh, you mean another regular expression, right? Yeah, that's true. That's true. That most likely, I mean, it's very likely you have to recompute, and so change is problematic. Yeah, it's a very good question. So, but this one is not, this basic shadow encoding is not optimal. We just basically show that there's an encoding that will work. So the optimal encoding is we propose an optimal encoding algorithm. We use a Huffman style coding. So basically we don't need really binary code. We only need prefix free coding. So basically, for example, the code assigned to 1, 2, 3, and 4, none of them is the prefix of another code. So as long as we have this property, that will be fine. So basically, I will skip the details. Basically, we first do this encoding for every subtree. We look at state 1 right now. We look at the root right now. So and then right now we have state 1, 2, 3, and 4. And so right now, the number of code right now is 0, and 2 is 0 right now, and 3 we have one bit already, and 4 we have 2 bits. So we can build a Huffman tree. So basically, after we build this Huffman tree, then we can assign the code. So in this way, the Huffman style code for state 1 is 0, 0, 0, and for 2 is 0, 0, 1, and 3 is 0, 1, and 4 is 1. So and then we use this code. So basically, you can see that this will also be a valid shadow encoding. However, we only need 3 bits instead of 4 bits. And we prove that this algorithm will produce the shortest code length. Okay, so next is about minimizing incomplete 1D table. So basically, after state P is deferred to Q, so we can one option is that we can remove all the common entries in P. So for all the common entries shared by P and Q, because P deferred to Q, and P will be table for P will be above Q in the TCAM, so we can delete all the common entries in P, and then the state P's table becomes incomplete. State P's table becomes incomplete. So one algorithm that we proposed is the weighted 1D incomplete table minimization. So basic idea is that we add one rule at the bottom will match everything for this table, and then we assign very high, extremely high weight, and then we do the 1D optimization because it becomes a complete table, and so that that optimization algorithm will guarantee that the last rule stays the last, and then after running that algorithm, we can delete the last rule. So, however, actually this is non-optimal because of basically, if you keep some deferrable transitions, if you keep some transition that you don't defer them, actually they can help in minimizing the incomplete table. So we have a partially deferred incomplete 1D table minimization algorithm. So here I just show you the possibility. For example, so suppose you have for this table, those one we in the shadow, those gray entries, suppose they all can be deferred. So if we delete all of them, so actually we will end up 2 entries. So one is this green, and another is these 2 entries will combine into by replacing the last 1 bit by star. So actually, if we for this defer transition in the middle, if we keep them, actually, if we keep this instead of deleting it, actually you can see that actually we can all combine them into one entry. This will be 0, 1, 1, 0, 0, 0, star, star, right? So basically, keep some of them not deferred. It may help, and we have a optimal algorithm for doing this, for achieving this using dynamic programming. I will skip the details on that. So another idea for minimizing TCAM table, TCAM space is table consolidation. So the basic observation is that so even after many common transitions are removed, so in the shadow encoding, so some transition tables they may also share common entries, for the input character column, However, for those entries, the source IDs are different and the destination IDs are different. The only same thing is the input character column. So what we want to do is that we want to still further remove such redundancy. So how to achieve this? We basically, for example, take a look at this example. If right now, so this state, one state has 3 entries, another has 2 entries because others are deferred. So if we pull, so you can see right now is this the first entry of the first table and the first entry of the second table is the same, and also the second one is also the same for in these 2 tables. So if we pull the other deferred entry back for the second table, and we could merge them, what will happen is that in the destination state field, we will need to have 2 columns. We'll have 2 columns. So one for the destination state ID for one table, and another column is for another table. So, and then the source ID, we can encode them by the same ID. For example, suppose we map both state ID 10 and 01 both to 0, for example. And so in this way, we basically further minimize the TCAM space. We use a little bit more SRAM space, but the SRAM is much cheaper than TCAM. So there are 2 technical challenges for doing this table consolidation. One is, so which states should be consolidated? So which 2 state tables need to be consolidated? So we have a global state consolidation algorithm. Another is, so given K tables, so how to merge them? We have a local state consolidation algorithm. So consider the previous example, we have 3 states. So if we all consolidate them together, so we further reduce the number of entries from 7 to 5. And in practice, if we do 2-state consolidation, every time we consolidate 2 states together, so this will result in about 16% to 49% of a reduction. And the best possible reduction will be 50%. So basically, I mean, any 2 can be merged together. That will be the best. But our results are close to that. So the global state consolidation algorithm. So basically, we basically want to find which two states need to be consolidated together. So to keep the benefit of shadow encoding, if 2 states are consolidated, so their parents also need to be consolidated. Here the parents is the deferment forest parents. And so basically the consolidation is based upon the deferment forest. And so basically you're given 2 trees, two trees in the deferment forest. We first merge the root, and then for their children, we need to find the one-to-one mapping, right? So which 2 states, which state map to which state will consolidate with which state in another tree. So we do this in like a brute force fashion. So basically, we build a biparty graph. So on the left column, left side is all the states, all the children of this root, and this on the right is all the children of this root. And when the state number of children are different, so we can use a dummy node, and then we compute a complete biparty graph. And for any 2 pairs from left to right, we compute basically the cost of merging these two. And then at the end, after we do this computation, we basically find the minimum biparty matching. And plus the cost of merging the 2 roots, that will be the optimal merging of the 2 trees. Another question is which 2 trees we should merge together. So which 2 trees we should consolidate. So we also do this like in a brute force fashion. So basically, with every tree as a node, we build a complete graph. And then for any 2 pairs of trees, we compute what's the cost of consolidating these 2 trees. And then at the end, we try to find a minimum matching in this complete graph. That will be the optimal state merging. And local state consolidation algorithm. So basically, here there are 2 points we want to make. So one is for any input, the transition in the merge table is deferred if and only if the corresponding transition is deferred in all the k tables. If there are k tables, there's some transition are deferred different different table defer different transitions. So we have to make sure that if all these tables defer this transition, then we can really defer this transition. Otherwise, we have to pull it back. So and for non-deferred transitions, after you do this, then that will be then the merging is very simple. Then basically the decision is the combination of the k decisions. So local state consolidation algorithm is pretty simple. Okay, so next we'll talk about the idea for increasing throughput. So basically, this idea is called variable striding. So the previous work, people considered k-stride DFA. Basically, every time they consume k characters in each transition, and this will end up exponential increase in space. So first, the transition as they have a transition explorer, because every edge used to be 256. Right now, it will be 256 to the power of k. For example, if you have 2 stride to the power 256 to the power 2, if you have 3 stride to the 256 to the power 3. And there is so that's first is state exploring, that's transition exploring. And second is there's also a state explorer. The number of states will explode pretty quickly. Basically, the number of accepting states will be equal to n times 2 to the power of r. R is the number of all the regular expressions. Well, if you have 100 regular expressions, that will be 2 to the power of 100. So that's pretty big. The rationale basically you have a DFA, and then if you go k steps, so consider this particular node. Consider a particular node. So there are many paths can go to. There are many paths can go to this. There are many paths can reach this state, and then during those paths, so there could be all possible combinations of there could be all possible combination of regular expressions are matched during that path. So that all possible combination is 2 to the power of r. So this formula is a little bit different from the previous published results. Were also similar to n times 2r, but they limit n is the number of non-accepting states, but I think it should be all the number of states. Okay, so the idea of k variable stride DFA, basically every time we consume a variable number of characters, we consume from 1 to k characters in each transition. This will lead to the goal is to have a linear increase in space to avoid these explosions. So this TCAM layout will be a 4 variable stride DFA. So take a look at this example. So right now the buffer is so here's the input buffer, and because every time it's 4 variable stride DFA. So every time you take 4 characters at a time, you take 4 characters and you perform a lookup, and the lookup result will give you 2 things. One is what's the destination state, and how many characters are consumed. So in this case, this is 1 stride, so we consume 1 character in this step. So then you basically move, you consume 1 character, and then you get another 4 characters, perform a lookup. So this time we'll consume 4 characters, and then you go again, and you get another 4 characters, you perform lookup. So this time will be 3, for example, and you move 3, and so on. So that's the basic idea. And there are 3 technical challenges here. So first is how to eliminate state explosion. So our solution is basically we expand along all the paths. So until we reach an acceptance state. So once we reach an acceptance state, we will terminate there for that path. And second is how to control the transition explosion. The number of transitions is huge. So we have two algorithms. One is self-loop enrolling algorithm. Another is k-variable stride transition sharing algorithm. So third problem is which state to expand. So actually we can expand any states for to have multiple strides. And so we have a variable striding selection algorithm. So first, take a look of self-loop enrolling. So the base. Okay. So that's the basic idea of variable striding. So I will ignore the details here. So let me show you some our experimental results. So for one stride, so we use four regular expression sets that are used in previous work in our experiments, and so with only transition sharing, we can achieve 1.18 to 2.07 TCAM entries per state. And with table consolidation, we can even bring the number of entries per state below below 1, less than 1. So, and for variables, 7 variable striding, so the self-loop enrolling will basically, it works better for uniform traffic, with traffic with few matches. And the variable striding algorithm will work well with traffic with more matches. So I will skip the details here. So the key contribution here is we propose the first TCAM-based regular expression matching algorithm, and we propose two ideas for minimizing TCAM space, and one idea for increasing the lookup throughput. And so we implement this and conduct it as experiments. And the work on it, based on this work, is published in Using Security this year. All right, thank you very much.
Any questions? Since it's already late, so maybe if you have a question, we can take it offline.
Okay.